Hello student friends, welcome back to lecture number 6 in this series. In this lecture, we are going to discuss types of limit states. In last lecture, we have discussed what is the meaning of limit state and the limit state method. So today we'll discuss what are the types of limit states. So the limit states are having three major types as specified by IS 456 under clause number 35.1. The first type of limit state is limit state of collapse. Second type is limit state of serviceability and other limit states. These are the three main limit states which we are going to discuss in detail in one by one. So let us discuss the first type, that is limit state of collapse. So this limit state of collapse have been provided under clause number 35.2 of IS 456/2000. On page number 67, they have mentioned this clause. So let us discuss this clause in detail. The limit state of collapse is reached when the structure as a whole or part of the structure collapses. It means that the collapse of structure may be taken due to the collapse of any one component, just like it may be a column, it may be a beam, or it may be a slab, or the total structure, that is a total building, may be collapsed. That at that time we can say that the limit state of collapse is reached. This collapse may occur due to the rupture of one or more members, or on account of formation of mechanism, or due to elastic or inelastic stability, or from loss of equilibrium, etc. There are many causes for the limit state of collapse. This rupture may be takes place due to the failure of any one member, just like it may be the failure of column, failure of beam. Again, that failure may be takes place due to failure of any one material, just like it may be due to the whatever concrete that we are going to use. That concrete may be not able to sustain the stresses. If the permissible stresses, or if the stresses which are actually coming on that component exceeds beyond the permissible stresses, then that particular member may get fail. So that particular instance is called as a limit state of collapse. So this limit state is taken care of by providing a resistance greater than the forces to which it is subjected, and keeping a margin of safety through factor of safety. So we can provide the safety, or we can achieve the durable and structures which satisfy the all conditions by providing the resistance greater than the forces. It means that the resistance offered by the members should be always more than the forces which are exerted on that particular member. So that can be achieved by adding an additional loads, or adding an additional strength to the members or to the materials by using safety factors, which we are doing in case of limit state method as discussed previously. So this resistance to bending, shear, torsion and axial loads at every section shall not be less than the appropriate value at that section produced by the probable most unfavorable combination of loads on the structure using the appropriate factor of safety. Okay, so that's why the IS 456 specifies different factor of safeties and the combination of these factor of safeties for different loading conditions. The limit state of collapse deals with the failure due to flexure, compression, shear, torsion and tension. So these are the different possible modes or the forms of failure. So let us discuss all these types of failures one by one. So flexure. So for this understanding that what is the exact meaning of flexure, that flexure is nothing but a member which is subjected to two types of stresses at the same time. It means that suppose if for instance, let us consider there is one piece, plain cement concrete beam which is simply supported on the two supports, and at present there is no external load acting on this member, so that we can say that there are no stresses. Particularly at this instant, no stresses are acting on the member. But suppose if an external load is going to act on this beam in the form of a point load, so due to that loading, this beam will bend like this. It will deforms like this, and due to this deformation, what happens that, as we have discussed previously also, these topmost compression fibers, these top compression fibers will be subjected to compression, and the bottom fibers will be subjected to tension. Okay, so it means that above the neutral axis, the compressive stresses are going to form, and below the neutral axis, tensile stresses are going to form. It means that two types of stresses are exerted in the member. So that's why such situation is called as a flexure. And mostly what happens, the failure of beam or failure of member will take place in case of flexure, just like the formation of cracks will start at the soffit of the beam or at the bottom of beam, and if the loads exist, that whatever loads acting on that beam, if those loads are continuous to act on that element, then these cracks may propagate up to the top and the failure may occur. So you can see one more example, that this is a cantilever beam, and as previously in this case, as we have seen that the beam is simply supported and the load is acting at the center, and due to that load the beam is deflected as shown in the figure, and the compression and tension are formed in the top and bottom portion of the section. Now in case of cantilever beams, what happens that suppose if this cantilever beam is subjected to an point load which is acting at the end, then what happens, this cantilever beam will be deflect like this. So in this case, what is the exact condition, that in this case that the topmost compression, top fibers will be in tension and bottom fibers will be in compression. So exactly reverse conditions are there as the previous case, as compared to the previous case. So in this case, up above the neutral axis there will be tension, and below the neutral axis there will be compression. So these conditions are called as a flexural conditions. So mostly the possibilities of failure of such kind of sections, that there may be possibilities of cracks here, here or here. So to avoid this, normally we are providing the reinforcement in the top portion. Okay. In case of beams subjected to simple support, the normal reinforcement is provided at the bottom portion. It means that it is to be provided in the tension zone. So we can say that this bottom portion of a beam is called as a tension zone, and as we know that the concrete is not able to carry the tensile stresses, so we have to provide the reinforcement in the bottom zone here. In case of cantilever beams, we have to provide the reinforcement in the top zone, that is in tension zone. This is the example of failure of beam due to bending. You can see clearly here that the cracks are started from the bottom in that, and it propagates to the top and it fell. Then living state of collapse due to compression in column. Here you can see that the column is failed due to the crushing of concrete. Excessive crushing is taken place, that as the load coming on this column exceeds beyond the permissible stresses, and that concrete is not able to sustain those kind of compressive stresses, and the column is bursted. That whatever concrete is present, that concrete is bursted. Bursting of concrete will take place. Here is also one more example. Here also you can see that the fear of pitch is fail. Here also the main reason is the bursting of concrete. That concrete, whatever concrete is present, that concrete is not able to sustain the stresses. Or the lack of confinement reinforcement is also one of the reasons that you can clearly see in this picture that whatever links we have provided, those links are not able to see in this portion. These links are not present here. So it will reduce the confinement, it will increase the confinement pressure. So to reduce that confinement pressure, the confinement reinforcement should be provided. So that's why due to lack of that, the column is filled. Then failure of column in buckling. If suppose the length of column is more, or we can say that if the column is a slender column, then the column may buckle like this. This is the example. And you can see here in this portion the concrete is also failed because this concrete is directly under compression, and those compressive stresses exceed beyond the permissible limit. That's why crushing of concrete is happen there. Concrete failure due to shear. As we know that the shear is maximum at the support, so that's why you can see that the shear cracks have been formed started from the support. So here it is the support provided, so the shear cracks are started from here. How these shear cracks are formed, how to reduce it, or how to restrict this, that we'll discuss in the limit state of collapse in case of shear, torsion and bending in detail. This is the punching shear. Punching shear of the slab may take place. This is also example of shear failure. Then concrete failure in torsion. Suppose if that any member is subjected to twisting movements, then there may be failure of that particular member due to the torsion. So you can see clearly the torsion is going to exert on this column, and that's why the concrete is failed. This is again the example of fear of a bridge, and mostly in case of bridges, as you can see here, the bridge is having only one column, and what happens normally is that whatever traffic is moving, this traffic is moving in these two directions. And suppose sometimes, many times it happens that traffic is only moving in any one direction. So as mostly the traffic is moving in this direction, so due to this there will be a twisting moment like this. So in such cases the column may fail. So all these points we have to take care while designing the members. So such things are producing here. So we'll stop here for this lecture. The remaining part we'll discuss in next lecture. Thank you.